Hey there, here we go into the last lesson in chapter 8 where we will be going over a very important topic in calculus called improper integrals. So what is an improper integral exactly? That would be an integral with bounds where one or both of the bounds either go to infinity or one or both of the bounds cause the function we're taking the integral of to go to a y value of positive or negative infinity. So essentially we're asking ourselves the question, what happens when our bounds are infinite or cause the integrand to approach infinity? Right? That's the question. And we have two answers. It's either the integral does what is called converge or we diverge. So what does that mean? To converge on something, right, is to meet at a set value. In math terms, that means that we meet at an agreed upon finite number. Right, so that's what it means to converge or meet on a finite number, one fixed value. To diverge is to go away from. That could mean that we're either going to an infinite value, or as you'll see in the distant future when we study this thing called series, it's in a little while, that's when we don't really agree on one set final answer. In these answers, it usually means that we're going off to infinity, or we can constantly change values again and again. Like if you took the area between sine x and the x-axis as we go on forever, it would never make up its mind because that area would keep changing again and again. So diverge means literally the opposite of converge. Converge means meet on a finite value. Diverge means don't meet at a finite value, often but not always going to infinity or negative infinity. And those are the questions. Now, before we get any further, I want to take a look at a graph of what this looks like. So let's say we've got the integral from 2 to infinity of 1 over x dx. So what does that mean? Well, we know that the area between the curve and the x-axis from this x value to that x value is what that integral means. So here's the visual. You start at 2 and we keep painting on and on forever. And the question is this area finite or does it basically increase without bound? And that's what we're going to find out next. But that's the visual. So let's do this. How do we solve that? How do we decide if this thing converges or diverges? And that's what the instructions say. Does the integral converge or diverge? If it converges, evaluate the integral, meaning find the exact area. Okay, so first things first, whenever you do these problems, it's important to note that we're not learning any new integration manipulations. However, it is important that you write out a limit because you can't plug in infinity. We can only approach it. So anything that causes either the function to approach infinity or actually has an x value going to an infinite value necessitates a limit. Necessitates. How about that? Very formal. So we take the limit as, and I shouldn't say x. I write that out there. We should say a or b or c. The reason why you don't want to put x is because we already have an x as a variable that's been defined. So the limit as a goes to infinity from 2 to a. And again, we have a bound that is approaching a value. We can't just plug in at the end. That's why we have to have the limit. Very important first step. Then all you're going to do is integrate like usual. First fundamental theorem, everything just like normal. And so this would be equal to the limit as a goes to infinity of, and then that integral is the ln of the absolute value of x, just like normal, integrated from 2 to a. And now we use the first fundamental theorem. It's not that bad. You literally keep the limit there until you evaluate it. The limit is a goes to infinity. And that's of ln of the absolute value of a, inserting the upper value in, minus the lower value. So again, same exact process as you've been doing, just keep that limit there throughout until we're ready to evaluate it, which is now. So now we're going to take the limit as a goes to infinity of ln of a. Well, that's essentially ln of infinity, right? And I know you can't plug in infinity, but this is the idea of what's going on in our brains. And so what's the ln of infinity? Well, we're really thinking e to the what equals infinity. That would be e to the infinity. So that means that this value approaches infinity minus ln2, and that ln2 doesn't mean anything. You subtract that from infinite amounts, it's still infinite. And so that means since our area will continue to go on and accumulate until we get to an infinite value, we say that this integral diverges. So that means that this area would keep going on and 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 on. Never stops. So that would be a diverging or divergent integral. It would converge if we got a finite number out of this. Okay, so let's now take a look at an example of something that, I'm going to do a spoiler alert here, converges. So that would be something like the integral from 2 to infinity of 1 over x squared. Okay, So now what we're doing here is we're finding the area from 2 to 1 over x squared. Now what you might notice here is the difference between this graph and that graph. They're graphed on a very similar window, and yet this area does not get tamped down, if you will, by the curve 1 over x as fast as 1 over x squared seems to tamp down the area. So maybe that will affect things. As I said, this one is going to converge, but let's see why. So we get the limit as, and again, I'm going to use a, as a goes to infinity. Pick any letter but x. So limit as a goes to infinity from 2 to a of 1 over x squared. I'm going to rewrite that as x to the negative 2 to set ourselves up with an integral. And so now we take a limit of that. The integration's not that hard at all. And so we've got the limit as a, or a, goes to infinity of, well, we're going to integrate that. We'll add 1. And then, of course, divide by that negative 1. And we'll evaluate that from 2 to a. All right, so let's evaluate away. So that is equal to the limit as a goes to infinity of negative 1 over x. So it'd be negative 1 over a, evaluating a into there, minus a minus. So minus a minus 1 over x. And again, the 1 over x is because it's x to the negative 1. Now, that 1 over x should be 1 over 2, right? It gets replaced with that. A little bit of action there. So that 1 over x gets replaced by 2. And now we evaluate the limit. So this is just a constant. But the limit as a goes to infinity of this, well, something's going to happen here. We're going to get the limit as a goes to infinity of all of that. And you know what? We're taking the limit itself. So I don't have to write that down again since we're taking the limit. We're going to get negative 1 over infinity. Nice. Plus 1/2. So we don't actually have to write the limit again. A little lesson for you because we're evaluating it here. Now, if I have a constant value over infinity, that goes to 0. So that ends up being 0 plus 1/2. And so the answer is the integral converges to this number. So your conclusion is we have a converging integral, and the area as, well, x goes out to infinity is 1/2. So this area here is 1/2. And you might be like, wait, that's 1/2, yet this goes to infinity? That's right. Basically what's happening here is we're not going down fast enough, the curve, 1 over x. So when you're adding on all these little areas, you're adding just enough to round up every little decimal place along the way, causing a domino effect to eventually add up enough. And remember, you're going out to infinity, you're adding up enough quick enough to go to infinity. This, however, does not add significantly higher area values. 1 over x squared gets closer to the x-axis quicker than 1 over x. Quicker enough so that we converge to an area of 1/2. So this area from 2 out to infinity, 1/2. So in general, when do we converge and when do we diverge in this kind of an integral? Well, it's actually very eloquent, and we've actually already seen the tipping point of this. So when you integrate this, you would get the limit as, and we have an a down there, so I'll use b now, as b goes to infinity from a to b of x to the minus n dn, right? And so I'm just saying, and that should say actually dx right there, n is a constant. So dx. And now, once we have that x to the minus n dx, the question is, what in the world do we do to integrate this? Well, we add 1 like normal. So you get the limit as b goes to infinity of x to the minus n plus 1 divided by minus n plus 1. And now let's think about this. We are going to converge, of course, minus, right? So that's evaluated from, I should do that from a to b. So we got to think about this a little bit when we converge, when we diverge. So if we take the limit as b goes to infinity of, and we'd be plugging in b to the minus n plus 1 all over minus n plus 1, minus, and that would be a to the minus n plus 1 over minus n plus 1. Now this a value is constant. It really has no consequence right here. It's not making the denominator 0. So we've got to check out and see what happens here. What's our tipping point? Well, let's think about this. When n is equal to 1, right? If n is equal to 1 or less, so we're going to diverge there when n is less than or equal to 1. You might be like, well, why? If n is equal to 1, well, at 1, we're going to have ourselves a situation where we get 1 over x to the 1. That's the ln of x. So at n equals 1, we get ln of infinity, right? Because this wouldn't just be something that is now some sort of power, it's going to be ln, and then we plug in infinity, and that goes to infinity, right? So we diverge. So when n is less than 1, if you think about this, let's say that we've got like, I don't know, n equals 0, right? So if n's equal to 0, or n is equal to 1/2, or whatever it is, if you plug in 1/2 in for n, you now have something where you would have b going to infinity, that's going to infinity, and you'd have minus 1/2 plus 1, which would be to the 1/2. So that goes to infinity. So we need a number bigger than 1 to keep the x value in the denominator after we integrate. So n being greater than 1 is when we converge. And for those of you that are watching this, you're like, dude, I don't totally get this generalization. That's fine. It doesn't have to be for you. Totally. This is a little bit more formalized. The tipping point is at 1, though. That's what I would take away from this. So let's say that we pick something like n equals 3. Well, now you've got something like 1 over x cubed. And when you integrate that, your integral is still going to have something nice. You're going to have, I think, minus 1 over 2x squared, right, is what that integral ends up being. Because you have x to the minus 3, you add 1 to that and divide by what that number is. But as x goes to infinity, you're going to get negative 1 over infinity, which is 0. So as long as you keep your variable in the denominator, you converge. That happens when n is more than 1. You don't keep your variable in the denominator if the power that we started with is equal to 1 or less. That's it. All right, so I wanted to go over that generalization, but the main idea is, do we converge? Do we diverge? And take those limits, because you can't plug in infinity, not at least formally. All right, I'll see you in the next video. We've got some more different varieties of this. Stoked to see you there. Peace.